A highway in Japan doesn't stop at the coastline. You can drive it today, and instead of ending at the water, it drops under Tokyo Bay and keeps going. Halfway out, there's something that still feels unreal even when you know it exists. A man-made island where drivers can stop with water in every direction. And the strangest part is this: the hardest problem in an undersea highway isn't the sea, it's what happens inside a long enclosed space when there's nowhere for danger to disperse. So why does this road disappear right here? From above, Tokyo Bay looks calm, just a wide sheet of water between two dense edges of Greater Tokyo. But on the ground, that water behaves like a wall. On one side, you have the Kawasaki area in Kanagawa, on the other, Kisarazu in Chiba. For decades, getting across wasn't a straight line. If you stayed on land, you went the long way around the bay, through traffic that can turn a simple distance into hours. And if you tried to cross the water directly, you were back to a different kind of schedule entirely. That's the problem the Tokyo Bay Aqua-Line set out to solve. It's a fixed crossing that combines a bridge section with an undersea road tunnel, and it's been operating since 1997. Not as a concept, not as a futuristic proposal, as an everyday route. And then there's the detail that makes the scale register. On the route sits Umihotaru, a man-made island facility out in the bay, an artificial piece of land where drivers can stop in the middle of open water. It's physical proof that this isn't just a tunnel underwater, it's a system built to live there. Here's the key point to hold on to. The Aqua-Line isn't impressive because it's underwater. It's impressive because it has to be reliable, despite everything a bay can do to concrete, steel, and human schedules. So if the goal was simply cross the bay, why didn't Japan choose one straightforward answer, only a bridge or only a tunnel? Out on the bay, the surface can look harmless: gray water, a steady horizon, a scene that feels quiet from a distance. But engineers don't design for the calm day. They design for the day the bay stops cooperating. The first constraint is simple. The sea is not a stable environment. Salt hangs in the air, collects on metal, works its way into joints, and quietly turns time into a force. Corrosion isn't dramatic on camera, but it is relentless in real life. And then there's the instinct everyone starts with. If you need to cross water, you build a bridge. That feels obvious. But a bridge lives in the weather. It takes every storm head on. It is exposed, always. So you think, fine, build a tunnel instead. Put the road where the storm can't touch it. But tunnels have a different enemy. Not waves, not wind, air. In open air, danger can spread out. In a long enclosed tunnel, it can't. A simple analogy is a hallway versus an open field. In a field, smoke can drift away. In a hallway, it becomes the hallway. That's why long road tunnels treat ventilation and fire response as life safety systems, not comfort features. So the trade-off becomes real. Above the water, you fight storms and exposure. Below it, you fight the physics of confinement. And the most fragile points are rarely the middle. They're the transitions, where one structure hands off to another and failure isn't gradual, it's immediate. Once you understand those constraints, the Aqua-Line's shape stops looking like a gimmick and starts looking like the only workable compromise. The first time you see it from the bay, it doesn't look like a single structure. It looks like a decision. Part of the crossing stays above the water as a bridge, because sometimes the simplest answer really is to stay in the open air. And then, at a specific point, the road does something counterintuitive. It stops fighting the surface entirely and disappears below it, becoming an undersea tunnel. That hybrid shape is the Aqua-Line's real signature. It isn't a tunnel under the ocean. It's a bridge and tunnel system designed around the moment the environment changes from wind and waves to confinement and air. And this is where Umihotaru matters. Because it's not just a dramatic landmark, it's a visible reminder of what this kind of project always needs: places to manage operations, safety, and the reality of running a long enclosed road underwater. Even if you never think about it while you're driving, the system has to. If you only watch 1 minute of this episode, make it the next one, because this is where the story either becomes ordinary or becomes impressive. To understand how something like this is built, you have to stop imagining one heroic moment, someone digging a tunnel under the ocean, and start thinking in steps. Undersea infrastructure is never one act, it's a chain, and every link is designed to remove one specific way the sea can win. Step one is the part nobody romanticizes, understanding what you're building into. Under a bay, the ground is not a neat layer cake. Conditions change. The only safe way forward is to map and plan section by section before you commit to anything permanent. The goal isn't just can we build, it's what will the ground do to us over decades. Then comes the work that looks straightforward but never is, creating stable supports and approach structures in a marine environment where salt, moisture, vibration, and weather are always present. Even when nothing is moving, the structure is being stressed by temperature changes, by traffic vibration, by wind, and by time. And then you reach the part people think is the whole story, the undersea road space itself. Here's the safe way to describe it without pretending we have a full technical dossier in front of us. Engineering references describe specialized undersea road tunneling methods for crossings like this. Heavy civil engineering built to be sealed, drained, inspected, and maintained. Not a glass tube, not a fantasy corridor. A working road space designed to stay controlled while the bay sits above it. A useful analogy is a submarine hatch. The magic isn't that a hatch exists, it's that it keeps sealing day after day through pressure changes, vibration, and wear. Undersea infrastructure is built around that same logic. Seals, joints, interfaces, inspection access, those are not side details. They are the project. And here's what most summaries skip. The delicate engineering isn't always in the middle of the tunnel. It's where the system changes, where one structure hands off to another and tolerances get unforgiving. So far, we've built the logic in layers, understand the ground, build the supports, create a controlled road space, and protect the transitions. Now comes the part that decides whether the crossing is merely impressive or genuinely safe. Because once the structure exists, the job shifts from construction to control, managing corrosion, drainage, monitoring, and response, every system that keeps undersea from turning into unstable. And that brings us back to the reveal we teased at the beginning. The most dangerous failure mode in a long tunnel isn't water arriving all at once. It's what can spread faster than water ever could. Once the Aqua-Line exists, the story stops being about concrete. It becomes about control. Because in an undersea road tunnel, the ocean above is a known threat. The structure is built to keep water out. That part is foundational. The harder problem is what happens inside a long enclosed space when something goes wrong, especially if it happens fast. Think of the tunnel like a sealed container. In open air, smoke and heat can spread out. In a confined space, they concentrate. That's why modern road tunnel safety focuses on 3 non-negotiables: moving air, detecting incidents early, and making response and evacuation decisions predictable. Ventilation is not about comfort, it's about survival. Air has to move in a controlled direction, fast enough to keep conditions tenable and predictable enough that emergency procedures still make sense. Monitoring matters because a structure like this isn't operated by hope. It's operated by sensors, procedures, and constant awareness. Small problems need to be identified before they become chains of failure, and response logic matters because in a long enclosed route, you don't improvise your way out. The design has to make the next safe decision obvious: where to stop, where to go, what to avoid, and how to keep people away from the worst conditions. That's the payoff to the open loop. The most dangerous failure mode isn't water arriving all at once, it's smoke spreading through a space that can't let it dissipate. If you only remember the headline, "Highway Under the Bay," you miss the real achievement. The real achievement is the invisible system that makes undersea feel ordinary. Now we reach the line between what we can state with confidence and what we should label carefully, because not every number people repeat online is actually confirmed. At some point in every impossible project story, the internet starts filling in blanks. Someone posts a number with confidence, someone else repeats it louder, and suddenly the facts feel sharper than the evidence actually is. So before we close this case file, we draw a clean line. Here's what we can say with confidence. The Tokyo Bay Aqua-Line is a real fixed crossing that combines a bridge section with an undersea road tunnel. It links the Kawasaki side in Kanagawa to Kisarazu in Chiba. It's been operating since 1997, and on the route sits Umihotaru, a man-made island facility out in the bay. Those are the anchors. Now here's what we should label carefully. Exact figures, like the deepest point of the route or the precise cost, circulate online, but without an official spec sheet in front of you, the safe wording is simple. No confirmed figure is publicly available in a single reliable place. If evidence is limited, we treat it as limited. A quick analogy is describing a skyscraper by guessing its height from a photo. You might get close, but close is not confirmed. And this is where most videos lose the plot, because the real story isn't a mythic number, it's the design logic you can actually verify. Ranked by likelihood, the most reasonable explanation for the Aqua-Line's shape is also the least glamorous. It's a hybrid because hybrid is what you build when you're balancing competing risks. A bridge gives you open-air simplicity in some sections. A tunnel gives you protection from surface exposure in others. The project isn't trying to be dramatic, it's trying to be reliable. The biggest myth is the sci-fi version, a glass tube under the ocean with views of the water. This isn't that. This is heavy civil engineering, designed to be sealed, ventilated, monitored, and maintained. And if that sounds less magical, it shouldn't. Because making the impossible feel ordinary is the entire point. Above Tokyo Bay, the ocean looks ordinary. Below it, a highway runs through a space that only works if everything you can't see keeps working too. The Aqua-Line isn't a miracle because it goes underwater. It's a miracle because it makes risk feel routine, by turning air, smoke, corrosion, and maintenance into a controlled system. And the most honest part of this story is also the simplest. Some details are easy to verify, and some require official specs we don't pretend to have. So here's the question I want to leave you with, because it changes how you see every impossible build after this. What do you think is the hardest problem to solve under the sea, water, geology, or fire and smoke? Next, we'll map another engineered place where the environment sets the rules.